Yesterday we introduced the idea of work. Who can tell me what work meant? Yep. Good. It's the change in energy of an object, the change in energy. So we can say, right away, we can say W is equal to delta E. Now, there were a couple things that were required for work to be done. In other words, a couple things that were required to change the energy of something. Okay, Elaine's desk is sitting right here. It's not moving. It's not above the ground. It doesn't have any energy. Okay, in order to give it energy, I got to cause this thing to move. How do I cause it to move? What do I got to do to it? How do I give his desk energy? Yep. Yeah, I got to push it. I got to apply a force. If I push it, then I can cause it to move. I've increased its energy, therefore I've done work on it. So force is required in order to do work on his desk. But it's not just enough to push on his desk. Right now I'm pushing on his desk. I'm not changing its energy, right? It's not moving. What else has to happen? Not only do we need a force, we also need, starts with an M or a D. Yep. We also need a displacement. We also need movement. Okay? It comes back fundamentally the definition of work, the change in energy. His desk doesn't change energy if I don't push on it, and his desk doesn't change energy if I don't move it. So it requires a force and displacement to change its energy. Therefore, we can extend this equation, W is equal to delta E, to become W is equal to delta E equals F times displacement. Now, the one thing about this is that it assumes the force and displacement are in the same direction. Sometimes they're not. If they're not in the same direction, we have to find a component of the force that is in the direction of the displacement. The nice thing about this is that on our data sheet, they give us the component already. We don't need to do that vector analysis like we have a number of times with other topics. They tell us we can find the component of the force that's in the direction of the displacement by tacking a cos theta on the end of it. Theta stands for what? Obviously, it's an angle, right? But what angle? Maybe. Theta stands for, anybody have a bit of a better answer there? What angle are we talking about there, Tara? The angle between the force and the displacement. So for instance, if I'm pulling a wagon this way, but yet it moves this way, that's my angle that I want right there. Okay, if I pull a wagon up a hill at this angle, say theta, what's my angle that I use right here? Somebody said 0? Why is it 0 degrees right there? Let's say our angle is 30 there, and our angle is 30 here. Why would I use 30 degrees in my equation when I'm looking at this situation versus using 0 degrees in my equation when I'm doing this situation? The angle is 30 degrees in both of them, right? So what's the difference between those two problems? Why would I use 30 here, but why would I use 0 here? How did we define that angle again? It's the direction or the angle between the way that it moves and the direction that the force is applied. Which way does it move here? To the right. Which way is the force applied? 30 degrees. What's the difference between those? 30 degrees. Which way does it move here? 30 degrees. Which way is the force applied? 30 degrees. What's the difference between those two? 0 degrees. Therefore, we're not going to use any angle right here. The angle would be 0 degrees. What's cos 0 again? Cos 0 is 1. So if the angle is 0 degrees, then we can just take off that cos theta, and the equation becomes delta E equals F times D. So if you've got an angle that matters, like you do in the first case, then tack on the cos theta on the end of it. If you don't have an angle, or it's an angle that doesn't matter, like in the second problem here, then just drop the cos theta and solve it using F times D. Is that good? All right, let's take a look at our homework, which is on page 294, questions 1 to 4. Any issues with those 4 questions? Jace, 4? Okay, any others? Really? 2? Okay, 2, 3, and 4? Let's take a look at 2, 3, and 4 here. 2 says a force acts at an angle of 30 degrees relative to the direction of the displacement. Okay, that's telling us that the angle that we want there is 30 degrees. Okay. If it moves one way, then relative to that, the force is applied at 30 degrees. Theta is 30, not 0. We want to find the force that's required to do 9,600 joules of work over a displacement of 25.0 meters. We know that the equation for work is delta E, but we also know that it's FD, and in this case it's FT cos theta because there is an angle here. The delta E part of it isn't going to be relevant in this question. It's only the W is equal to FD cos theta that's relevant. So let's rearrange it. Let's solve for F here. Let's take the D cos theta over by dividing. W is 9,600 joules. Delta D is 25.0 meters. And of course, cos theta is cosine 30 degrees. Let's use some brackets on our calculator to solve this, okay? Let's say 9,600 divided by bracket 25 times cosine 30 degrees, and the bracket for the cosine, and the bracket for the denominator there. We should get a value of 443 newtons. And that should be, I hope, the answer that's given to us down here. It is 443 newtons. Okay? Can't remember who asked me for that one, but is it okay? Question 3 says a force of 640 newtons does 12,500 joules of work. Over a displacement of 24.0 meters. What's the angle? This one's harder. This one's harder because we've got to solve for theta. Clearly, if there's an angle, we've got to use the equation FD cos theta. And we've got to solve for theta. That's the tricky part of it right there, is solving for theta. Let's rearrange it to solve for cos theta first. Cos theta is W over F times D. The F and the D go over by dividing. Now we want to solve for theta. Anyone know how to do that? Anyone know how to solve for theta there? Yeah. Right, it's the inverse of cos. So we're going to say theta is equal to cosine inverse, or cosine on your calculator, cosine second function, W over F times D. All right, so we're going to say the inverse cosine of W is 12,500 over, do we know what F is? Yeah, we do, 640 times 24. Let's do this one on our calculator as well to make sure that we can get the right answer. Let's get what's inside the brackets here first, and then let's do the inverse cosine function of that, just so it doesn't become really cumbersome with our calculators here. 12,500 divided by, let's use some brackets here, 640 times 24. End those brackets. Press equals. Now it's what's inside the brackets. Now let's take the inverse cosine of that. I saw a lot of people doing this yesterday. They were retyping that number, 0.8138, and so on. What's the easiest way to do that? Instead of retyping that, second function answer. So it takes the inverse cos of the last number that you calculated, because it has to be 35.5 degrees. And sure enough, that's the answer that they give me. What was the issue with that one, guys? Was it the inverse cosine thing? Okay, you knew what to do, except you didn't know how to find theta mathematically. Okay, finally, number 4 says a bungee jumper with a mass of 60 kilograms leaps off a bridge. He's in free fall for a distance of 20 meters before the cord begins to stretch. How much work does the force of gravity do on the jumper before the cord begins to stretch? Well, work is equal to delta E, and it's equal to FD times cosine theta. Why did I drop the cos theta there? Why is that not important in this question? Which way is he moving? Which way is he moving as he falls? Downward. Good. What force is causing him to move downwards? Gravity. Which way does gravity act? Which way does gravity act? Downwards. So if he's moving downward and the force is downward, then what's the angle between the way that he's moving and the direction that the force is being applied? 0, right? So if the angle is 0, we don't have to put the cos theta in there. All right, we want to find the work done by gravity here. Let's use the force of gravity that we know is causing this thing to fall. That's going to be m times g, 60 times 9.81. The force times the displacement of 20 meters. 60 times 9.81 times 20, I assume gives us 1.18 times 10 to the 4 joules. How many people got that? Okay, now, there is another way to take a look at that. We could have used W is equal to delta E in this case, even though we hadn't done any practice problems with that at this point yesterday. The delta E could have been the final energy minus the initial energy. Okay, and we could have done the analysis with energy that way, and we would have got the same answer. Okay, but I don't think any of you probably tried that, so we won't bother. You guys did? Well, it does become the same thing as EP is equal to mgh, yeah. But here's why, right? If we said work is equal to the change in energy, what kind of energy do you lose as you fall? Potential energy. So the final energy would be 0. The initial energy would be potential. The change in energy would be the same, essentially, as the initial potential energy. Does that make sense? That's why it works out to be the same. Now, the reason I didn't talk about that as we went over it is because we hadn't really talked about the whole delta E part of work yet. And we're going to talk about that today. Yesterday we focused on the F times D. Okay, but it was solvable that way if you tried it that way. Okay, we've got a couple more examples, and a couple more examples that unfortunately don't appear in your textbook. So you're going to ask you to copy them down, and then we'll do them as a class here. So it says a 20 kilogram object gains 300 joules of kinetic energy as it's pushed a distance of 100 meters. What's the force used to push the object? Nowhere in this question does it mention the word work or energy. In fact, we don't have to use work and energy to solve this problem. We can go back to the old-fashioned kinematics and dynamics stuff that we learned earlier in this unit and back in Unit 1. But work also applies here. And it also applies because we're pushing something over a distance. We're increasing the energy, right? We're increasing the energy of something. We're doing work on it. We have a mass of 20 kilograms here. We have a change in energy, or a work, of 300 joules. We have a displacement of 100 meters. We want to find the force. We know that work is equal to delta E, and we know that it's equal to F times D. And we know there's a cos theta on the end of it sometimes, but we're going to assume here that we're pushing it in the same direction that it moves. Therefore, we can drop the cos theta on the end of it. We know that delta E is equal to W, and we know that we have that value. We know that we have the displacement. We can find the force pretty easily at this point. It becomes delta E over delta D. It's 300 joules divided by 100 meters. Our force is 3 newtons. Why such a small force? Wouldn't we have expected a bigger force here to push a 20 kilogram object? Well, look how far we're pushing it. We're pushing it 100 meters. We're not giving it very much energy. We're only giving it 300 joules. So it takes us 100 meters to push it, it takes us 100 meters to give it 300 joules of energy. It doesn't take very much force to do that. If we gave it a bigger force, it would have gained a whole lot more energy over a span of 100 meters. One more. This one says a 1,200 kilogram car accelerates from rest to 90 kilometers per hour. We're going to circle that right away, that kilometers per hour, because we know we're going to want to be in meters per second here, right? Over a distance of 200 meters, what's the work required to do this? And then what's the net force that's required to do this? So two questions here, really, right? We've got a mass of 1,200 kilograms. We've got a VI of 0 meters per second because it starts at rest. We've got a VF of 90 kilometers per hour, which we're going to want to convert to meters per second. How do we convert that? Don't try to convert it all at once, right? We're converting kilometers to meters, and then we're converting hours to seconds. How many meters in a kilometer here? It's 1,000, so it's going to be 90,000 meters per hour, or 90,000 meters per how many seconds in an hour? What is it? 3,600 seconds in an hour. That gives us 25 meters per second. All right. My displacement is 200 meters. We want to find the work, and we want to find the force that's required to do that work. We know that W is equal to delta E, and it's equal to F times D, and it's also a cos theta tacked on the end of it if the angle is something other than 0. But we can assume here, I think, that the force that's pushing the car is in the same direction as the car's movement. Therefore, theta is equal to 0. Therefore, cos theta is 1, and we can drop it. Let's find work first. Then we'll worry about finding F. To find work, we could either multiply F times D, but we don't know what F is, so that doesn't seem to work. Or we can use the whole delta E thing. What kind of energy does this car have at the end of the problem? After it's accelerated, it's got what? Sadie, what kind of energy does the car have after it's accelerated? Yeah, no, you're right. Yeah, it's kinetic energy. So we're going to say it's 1/2 mvf squared. What kind of energy did it have at the beginning of the problem? What kind of energy at the beginning of the problem here? What is it? Well, yeah, there's chemical potential energy, but we can't account for that. Yep. Static? I think you're thinking about forces and friction. Okay, what kind of energy do we have? Nope. Nothing, right? The car's sitting there. The car's just sitting there. So we're going to say 1/2 mv squared minus 0. At the end of the problem, it had a certain amount of energy. At the beginning of the problem, it had nothing. It did, you're right, Rucker, have chemical potential energy, but we'll focus on the kinetic here. 1/2 of mass is 1,200 kilograms times the final speed of 25 meters per second. We've got to square that. Minus 0, of course. So we get 625 times 1,200 times 1/2. 625 times 600 is 375,000, which we're going to round to 2 digits, which is 3.8 times 10 to the 5 joules. That's a lot of energy. And that last question we had, what was it, 300 joules? That's why not very much force is required to push this object, that ball, a distance of 100 meters, because we weren't giving it very much energy. Here we're talking about a car going to 90 kilometers per hour. It takes a lot of energy in order to do that. A lot of work to do that. 3.8 times 10 to the 5 joules. Finally, we want to find the force. Now let's go back to the other part of the equation. W is equal to F times D. We know what W is because we just found it. We know that force is W over D. So 375,000, the unrounded number, divided by my displacement of 200 meters. 1,875 newtons, which we're going to round to 3 digits again, or 2 digits, I should say, 1.9 times 10 to the 3 newtons. So in that last question, we applied A very small force over 100 meters on a very light object. Didn't do a whole lot of work on it. Here we applied a very big force over 200 meters, and we did a whole lot of work on this car. First question, a little bit trickier than what we did yesterday because we're not just multiplying F times D. We've got to do the whole change in energy thing, right? The change in energy is 300 joules. Okay, that's equal to work, and that's equal to F times D. We rearranged it to solve for F. This one's similar, but a little bit further because we don't know what delta E is in this one. Okay, we're not told what it is in this one. We've got to find it. But we know how to find delta E. Final minus initial. Okay, if we know the final is kinetic and we don't have any in the start, then let's subtract the two of those, get the change in energy, get the work, and then let's divide that by my displacement. Okay? Here's what I want you to do right now, please. There are no problems in the book that I want you to work on this right now. I'd like you to take a look at your worksheet, please, on work that you haven't got yet. So let me hand that out to you now. And I'm going to ask you to do that worksheet on work, which is the third worksheet in the booklet for you, okay? And we'll take a look at a couple of questions a little bit later in class after you've had a chance to work on them.